In this video, we complete the proof that the Gaussian integers form a Euclidean domain. We begin with a synopsis of the two previous videos. First of all, the Gaussian integers are defined to be the set of complex numbers where both the real and the imaginary parts are integers. They form a subring of the field of complex numbers. We have also defined a function u going from the set of Gaussian integers to the non-negative integers defined by u of a plus bi is simply a squared plus b squared. It turns out, and this is somewhat relevant, that u can easily be extended to the complex field, and then it winds up going to the set of non-negative real numbers. So this winds up going to all of the real numbers such that r is bigger than or equal to 0. And that's going to be relevant a little bit later on in this particular video. We have also, in the first video, proved that that nu of a product is actually equal to the product of the nu's. In other words, that nu of x times y is nu of x times nu of y. And if we have Gaussian integers, this particular equation will imply this particular property. And the reason why is that if we have x is equal to a plus bi and y is equal to c plus di, and x and y are not 0, then we know that a squared plus b squared is not 0, and because a and b are integers, that will actually imply that a squared plus b squared is at least as big as 1. Same thing for c squared plus d squared. The fact that c squared plus d squared is an integer that's not equal to 0 and is positive will imply that c squared plus d squared is at least as big as 1. This fact over here does hold for all non-zero complex numbers. And then it's also worth stating that this thing over here is the first property of an Euclidean valuation on the ring of Gaussian integers. But in general, this particular inequality is not true for all complex numbers, so nu is not going to be a Euclidean valuation on the field of complex numbers, just on the ring of Gaussian integers. In the second video, we started working on showing the second property for Euclidean evaluation. In particular, we were looking at x and y belong to the Gaussian integers, y is not 0, and we are needing to show that we can find a q and an r inside the Gaussian integers such that x is equal to q times y plus r, and u of r is strictly less than u of r is strictly less than u of y, or r is equal to 0. And in our quest to do that, we let x be a plus bi and y be c plus di, and we specifically said that y was not going to be 0, so that says c squared plus d squared is at least as big as 1. And we also observed that since y is not 0, y has an inverse in the complex numbers, and y inverse is given by this formula inside the complex numbers. And then we basically computed x times y inverse inside the complex numbers. And when we did, we got this ugly looking expression. And at this particular point, what we wound up doing is we said, well, these two things are rational numbers, so we'll let r1 be this rational number. And then we notice that a rational number is always trapped between two integers. And whatever they are, one of them is closer. And so for R1, we let m be the closest integer to R1, and s is going to be, and there should be a minus sign in front of that, s should be trapped between -1/2 and +1/2. And then we did the same thing for R2, and there should be a minus sign there as well. So R2 is this ugly rational number, but we're going to write it as n plus t, where n is the closest integer to R2, and t is trapped between plus and -1/2. Now, what that means is that we can now write x times y inverse as m plus s plus n plus ti, but that can be rewritten as x times y inverse can be written as m plus n I plus s plus ti. And that's where we want to pick up and consider what goes on next. So we have x times y inverse is m plus ni plus s plus ti. And what I want to observe is that this particular thing is indeed inside the ring of Gaussian integers. This guy is not, but this guy is. Now look at this. I can write x as being equal to x times y inverse times y. And I can put parentheses around that. And now I can write x as being m plus n times I plus s plus t times I. And what this lets me, times y, because all I've done is I've substituted this mess in for x times y inverse. So, okay, what does that tell me? That tells me x is equal to m plus ni times y, I'm distributing, plus s plus ti times y. And now I want to look at exactly what's going on here. I know that x is inside the ring of Gaussian integers. I know that this guy is inside the ring of Gaussian integers because m and n are integers. And y, of course, is inside the ring of Gaussian integers. This particular one term right here, I don't know. And I'm actually going to label this whole thing as r. So I'm going to let r be equal to s plus ti times y. If r is inside the Gaussian integers and has nu less than nu of y, then I'm done. But I have to actually worry about that. So now let's continue looking at some special things. This equation can be rewritten as follows. R is equal to x minus m plus ni times y. And this is inside z of I, and this is inside z square bracket I, and this is inside z square bracket I. In other words, these are all Gaussian integers, which forces that sum, that difference, to be inside the ring of Gaussian integers because the set of Gaussian integers is a ring. It is a subring of the complex numbers. And so what that does tell me is R is indeed a Gaussian integer. Now the question becomes, is nu of r less than nu of y when r is not equal to 0? Well, let's look at that. So we already know that r is equal to s plus ti times y, and I want to recall that if I think about nu as going from the complex numbers to the set of non-negative real numbers, that nu of alpha times beta is going to be nu of alpha times nu of beta whenever alpha and beta are both not 0. That was from the first video. And so what I want to do is I want to think about, what do I know here? Well, let's see. The first thing is I want to think about nu of r is going to be nu of s plus ti times nu of y. So what can I say about nu of s plus ti? Well, I want to note nu of s plus ti is going to be s squared plus t squared, and I know that minus 1/2 is less than s and t are both less than or equal to positive 1/2, and that says their squares satisfy 0 is less than or equal to s squared and t squared, and they're both less than or equal to 1/4. So nu of s plus ti is going to be less than or equal to 1/4 plus 1/4, which is 1/2. And what does that tell me? That tells me that nu of r is nu of s plus ti times nu of y, but this particular guy here is less than 1/2, so this whole expression here is less than or equal to 1/2 times nu of y, and that's going to be less than nu of y, since nu of y is known to be at least as big as 1, because y is a Gaussian integer and y is not equal to 0. So what this means is that we do now have the following. We have x can be written as m plus ni times y plus s plus ti times y, and we can set q equal to m plus ni because that's clearly inside the ring of Gaussian integers, and we can set r is equal to s plus ti times y, and we have already shown that that is indeed a Gaussian integer, and we have also shown that nu of r will be less than nu of y when r is not equal to 0. So nu does satisfy the definition of Euclidean valuation on the integral domain z square bracket I, in other words, on the ring of Gaussian integers. And that's enough to say that the set of Gaussian integers is indeed a Euclidean domain.